Hello wonderful person, this is Anton and this is the Moon. Now in today's video I wanted to actually discuss a new hypothesis that suggests that our moon was created different from how we actually thought about it before. So let's talk about science behind this discovery. Welcome to What the Math. So now that we've actually successfully destroyed our moon completely using one of these simulations in Universe Sandbox Square, let's talk about how this beautiful object was very likely created. Now the moon, as you know, is one of the biggest satellites in our solar system, and what's really interesting is that not only is it the biggest, but it's also one of the strangest, and I'll show you why. Let's actually take a look at some of the other satellites of other planets, starting with Mars. As you can see, Mars has two moons, but they're ridiculously tiny. Look how small they are. This one here is only about 11 kilometers in radius, and the other one is not much bigger. Venus and Mercury have no satellites, no moons, and Jupiter, Saturn, and other gas giants have quite a variety of moons, but all of them quite small. So like, for example, here's Io, the closest big satellite to Jupiter, which is actually quite comparable to our moon in size, but in comparison to Jupiter though, it is very tiny. So how our moon was created has always been a bit of a mystery, and the most prominent theory so far, or hypothesis that is the one I've talked about previously. It's known as the giant impact hypothesis, which you can of course check out in one of the previous videos I've made. But today we're going to be talking about the new hypothesis from 2017, specifically January 2017, known as a multiple impact origin hypothesis, also known as the moonlet hypothesis. Now let's talk a little bit about what this all means and why it's actually proposed and why we can't really settle for the giant impact hypothesis. So first is that both Earth and the Moon have a very unusual, very similar composition. The rocks on Earth are very similar to the rocks on the Moon. And we've discovered this when we landed the Apollo missions on the Moon and brought the rocks back, and we've discovered that they're just very similar, too similar, as if they were formed from the same object. And previously, the idea was that an object known as Theia, possibly somewhat similar to Mars in size, smacked onto our planet, and the fragments that basically escaped the explosion formed the moon. Now the problem with that hypothesis is that this would not explain the extreme similarity of Earth and the moon, and this is why the scientists are still struggling to explain how the moon was formed. This new hypothesis may actually explain this, so let's actually recreate this hypothesis using Universe Sandbox Square. We're going to start by creating a randomly generated rocky planet known as the Proto-Earth, and it's obviously going to look nothing like the actual Earth. And what we're going to do now is basically simulate the creation of the moon, or at least try to. So, according to the new hypothesis, this is what possibly happened. So during the so-called heavy bombardment era of our solar system, an object that was possibly about the size of the moon, maybe even bigger, closer to the size of Mars, impacted our early Earth, created a very beautiful explosion, and as a result of this explosion also created some kind of a debris field and very likely some kind of a ring around our Earth. And so here we're going to do this manually by adding a Jupiter-like ring around our beautiful planet Earth, or Proto-Earth in this case, just to demonstrate what happened. And all of this happened within days of the collision, so after a few days there was basically a ring orbiting around Earth. Now because this ring was in the unstable region, possibly very close to the so-called Roche limit, all of these particles on the inside either crashed back to the planet Earth or somehow disappeared into the outer solar system, but the particles on the outskirts started to coalesce into smaller pieces, into basically larger pieces, eventually becoming proto-moonlets, I guess you would call them, so bigger fragments that we're going to create right here. And so here we go, these slightly larger pieces started to coalesce on the outskirts, somewhere beyond the Roche limit, and started to basically create larger pieces. And eventually, only one piece remains. So we're going to kind of combine all of this into one large piece, just so you can kind of see what happens after several hundred years. So this would be not even thousands of years, possibly several hundred years that it would take for all of this to kind of combine into one large piece, with some pieces, as you can see, just flying onto the outer region and then possibly even disappearing completely from the nearby Earth space. So a lot of these pieces will either fall back to Earth or eventually disappear and possibly join the asteroid belt. So let's see what happens after a few years here. Alright, so it looks like a lot of these fragments actually came back to Earth, but some of the fragments are still orbiting around us. Alright, so then, what happened afterwards? Well, millions of years passed until another impact occurred. Impact number 2. And this is, of course, because there were quite a lot of fragments flying around, quite a lot of protoplanets in our solar system, because the solar system was still forming. And as you can see, there was actually a very large fragment that formed right there. And so this fragment, along with the newly formed ring that I didn't add this time, will eventually create another... Oh, there you go, there's the ring. Will eventually create another similar event where we'll have rings that will coalesce into fragments, and some fragments will fly away, some fragments will stay, eventually combining into one, possibly slightly larger fragment. Then, as you can imagine, millions of years later, another fragment does the same, and another fragment does the same. And this happens close to about 20 times. Now, as you will see in a few minutes, what will start happening eventually is, well, all of these fragments that were still kind of orbiting around our planet Earth and all of these rings will eventually start coalescing into a single large piece. Although maybe in this particular simulation, because this is all random, it might not actually occur, but the scientists who wrote this particular paper think that this is exactly what happened. And this would actually explain why the composition of Earth and the Moon is so similar, because these fragments are much smaller than one giant impact. These fragments are only releasing the material from the outside of the surface of our planet Earth, and all of these materials are very, very similar in composition. Obviously, a lot of the stuff stays on the planet, and especially things that are heavier like silicates and metals will most likely be deposited to the bottom of our planet Earth. But the lighter materials and the materials that get evaporated from the surface will stay on the surface of Earth and also will be released into the outskirts here, eventually creating or coalescing into a very large moon. And so I haven't really been counting, but let's just do maybe 3 more and let the simulation run for a few years now. So this is many, many millions of years, possibly even hundreds of millions of years, because a collision is not very, very common. As a matter of fact, planetary collisions are extremely uncommon. We haven't really seen any just yet. We might have seen one in the past 100 years or so, but even that one is questionable. So for a planet to collide with another planet, it's an extremely rare event. But the scientists think that this is exactly what happened in the early formation of the solar system. And after about 100 million years, after these 20 or so collisions, all of these particles coalesced into one large chunk. So over time, all of this will combine into one large moon that we now added right here. And as this piece grows larger and larger, it will attract other particles or throw away particles that were too small and basically clear the area, clear the orbit of everything else present. And so essentially, this is what this particular hypothesis suggests. Now, it may actually seem a little bit more improbable than just one collision, because one collision is, it's not very unlikely to happen, whereas 20 collisions is extremely rare. But at the same time, because these are smaller pieces and because this is an early formation of the solar system, This is actually a pretty interesting theory, a pretty interesting hypothesis, because it does explain very well why the composition of Earth, which I should probably maybe cool down a little bit now. Let's make it about 100 degrees. The composition of Earth that you're about to see in a second, and the composition of Moon that orbits around it is extremely similar. And as you can see, we now also have liquid water on the surface. So maybe this is actually how the water was deposited on the surface of the planet as well. So all in all, this is actually a pretty cool hypothesis if you ask me, and definitely a really interesting explanation to how our beautiful moon may have actually been formed and why it's so similar to our actual planet Earth. At least in terms of the composition of regolith, or also known as rock. But you know what, in the next video or one of the future videos, we're going to explore all of the hypotheses for how the moon was actually formed, and I'll talk about some of the other crazier ideas as well. Anyway, thank you so much for watching, and hopefully you enjoyed this video, and if you did, don't forget to subscribe, don't forget to share this with someone who enjoys learning through video games, and possibly even consider supporting this channel on Patreon, because it does help us grow a little bit every time. I'll see you guys in the next video, space out, and as always, bye-bye. And let's just accelerate time and see what happens to our beautiful, strange, unusual Earth system with the moon orbiting around it.